Greetings from high above Grand Park overlooking scenic Westfield. It's my solution to question 8.40. Well, guys, this question tries to bring a few things full circle. In the last chapter, we did a question that involved looking at HIV testing. So here's a situation where we can use binomial probabilities to continue to say something about such testing. So let's say that there are 20 units of blood that have AIDS antibodies present in them. And we'll call X the number of units of blood out of 20 that are detected in this particular blood bank. So it is reasonable to say that X is distributed binomially, B for binomial. The count is 20 because we're trying to detect out of those 20. And the success probability is 0.99. So we have a test that 99% of the time, if antibodies are present, the test will indicate exactly that. So there are two outcomes. Either we have a positive or a negative test result. Positive meaning the antibodies were detected, negative meaning they weren't detected. There's a fixed number of trials because we are only trying to detect these 20 particular units. The probability of success is 0.99. And we are assuming that the test is independent. So whether or not the test has a correct outcome for any trial is independent of whether or not that outcome is correct for any other trial. So in part B, we are looking for the likelihood, as we would hope, that the count is 20, that all 20 are detected. So we're also looking for the likelihood that all 20 are not detected. So the first value can be found using the Binomial Pdf command. So let's pull that up on the calculator. So the Binomial Pdf command, second variables, depending on the version of the calculator you have, it's either option A or B, so you could hit the alpha key and go straight to that option. My Binomial Pdf command is option A, so I'll press enter. The number of trials is 20. The success probability P is 0.99. And I am interested in detecting all 20 of these units that have HIV antibodies or AIDS antibodies present. So that likelihood is 0.818, if you will. So at some level, it's surprisingly small, given that the test is supposedly accurate 99% of the time. We are only able, though, to detect all 20 of them about 82% of the time. So what is the likelihood that we will not detect all 20? So that's simply the complement of this event up here. So it's approximately 1 minus 0.818. Again, I'm using approximately because I have rounded the 0.818. So that shouldn't be particularly difficult to do. That's 0.182. 0.182. So nearly 20% of the time, we won't be able to detect all 20 of those units. Nearly 20% of the time, at least one of them is going to get through. Hey, something to think about too. If you wanted to, you could also calculate this. This is the same as the probability that the count is X is less than or equal to 19. The count that we detect is less than or equal to 19. And again, that is a less than or equal to count probability. So this is something that we could use the Binomial Cdf command to do. So briefly, let me just go back to the calculator and review that with you. On my calculator, I believe that's option B. So I'm going to use the shortcut and go alpha B. There it is. I can see I've got the right one, Binomial Cdf. Now again, depending on the version of your calculator, the shortcut key might be a little different. So you should take a look. So there are, again, 20 trials. The success probability is 0.99. And I'm interested now in a value of 19 or less. I'm interested in all of those counts, 0 to 19. What are their likelihoods combined? So again, there it is, 0.182, just like we already saw by using the complement rule. So going back then, next part of the question, part C, what is the expected count? So on average, how many would we typically tend to detect? And that would be the 20 times the 0.99. That comes up to 19.8. As we would expect, that's relatively close to 20. That makes sense because the success probability is so high. So in terms of the standard deviation then of our count here, I can take the square root of 20 times 0.99, the success probability times the failure probability of 0.01. So, and that comes out to be about 0.44. Oh, and we've come full circle. Notice we've seen that before. That's exactly the same standard deviation that we had in the very first question that we were looking at. I believe that was question 8.21, the first question out of this assignment, where, wow, this is a great example of how you can use exactly the same probabilities, but to model something completely different. We had 20 athletes that were graduating at a success rate, a graduation rate of 0.99, and we used this standard deviation. Notice it's a different scenario, but it's mathematically identical. So this time we have 20 units of blood that are AIDS antibodies present that we would like to detect with a success rate of 0.99. So again, there's our standard deviation of 0.44. So again, because the probability of success is so high, notice there's not a whole lot of variability. We expect to be pretty close to that expected value of 19.8 plus or minus about 0.4 units that may be detected typically. So small standard deviation because the likelihood of success is so high.